memes here. Yes, we're back, and of course, like many things, I had been listening to a video, and then I hopped on Wolfram Alpha to check a few things. So we're just going to go over some basics with black holes and stuff today. Link to the published Computational Notebook is in the doobly-doo below, of course. And well, let's just jump right into it. Black hole basics with Wolfram Alpha. We start off by typing in black hole, and we press enter. And when it works, it gives us use these different things, and it's assuming a formula. And again, full disclosure, this is the Schwarzschild metric. So we're assuming a non-routine, so we're not putting in the electric charge or angular momentum. Hey, Tom, thanks for joining, my friend. But what do we got here? All right, black hole. So we're just doing the basic formula here. All right. So now it's gonna have the math and everything, but don't worry, you literally just copy what it's there. You can literally just type the exact same things there. So we're gonna go over the properties. All right, event horizon radius, basically the part where you cross and you can't get back there. Horizon surface gravity, temperature, entropy, yada yada yada. Because all those fancy things there. If you want to do that, the actual full Schwarzschild metric, I don't even necessarily know what the full. I think is this the no? The Kerr metric has the two ones, but essentially, he was the dude in Germany that ended up solving it and then died a few months later. Einstein's like, hey, he just did a generalization. All right. So what we're going to do is the big thing here when you have all these things is the mass. Because as we know, like for a neutron star, it's the weird thing because it's all crushed down. You get like a whole bunch of neutrons and stuff. And when you add stuff, mass to it, it gets smaller. That's because it's getting more compact. But once you hit a black hole, it seems to be a place of maximal density, so to speak, as far as we know. And what it does is it slowly starts to grow and starts to grow. Tom will touch on that later. This is why I went into science. I'm trying to avoid being that guy, even though I do tend to encourage it. But we continue. So basically, we're just going to plug in the Planck mass there because you put in whatever you want. You put in whatever your own body weight in kilograms or whatever like that. But we're just going to do the Planck mass, which is like, I don't know, 22 micrograms. Basically, it's something that's really small to us, but if you work in the pharmaceutical industry, you're probably dealing with masses like that and maybe even less than all the time. All right, so the event horizon race, the plot, where if you cross, you can't get back over. What is it? 2 big G Planck mass, because we put in that mass there, divided by the speed of light squared. All right, so that's 2 gravitational constants times the Planck mass to the speed of light squared. Let's put it in. But, Rick, that's very provocative. Um, like Tom, we can talk later about that. But these are just, again, the basic things, assuming the Schwarzschild metric. Um, But okay. So, yeah, we have plugged that into Wolfram Alpha. What do you get? All right. You get 3.233 times 10 to the negative 35 meters. Wait a second. That looks like about twice a Planck length. Oh, look. It's 2 Planck lengths. Imagine I actually wasn't even sure, but apparently that's what the maths say. So it's like the minimal radius appears to be 1 Planck length. Um, Again, some people may disagree. But all right, so zero point 0.3 times the length of a putative string in M theory. Okay, so as soon as we can start hitting those energy levels of 10 to the negative 30, okay. But okay, the horizon surface area. There's a reason, and again, I am totally biased on one of the reasons I'm sharing this because anytime I see something that gets my noggin jogging, especially if it's something that could potentially help some of the things I'm working on out. Sure, I'm going to show it. But horizon surface there. All right, so we get that 16 pi times big G, the gravitational constant squared, times our mass component here, which would be the Planck mass down there. Just type it in, square it. That's all over C4. Not the boom kind, but the one that in nuclear processes, basically when you have big G over that. No, big G is before. Basically, it's like an inverse of the Planck force. Speed of light to the fourth. It's before convention. All right. So we put all that in there, and after I queried it the right way. We get that there. We get this. What is this? We get 1.3 times the negative 68 meters. What the heck does that mean? Well, that's what it means. 50 Planck areas. So it would seem, at least according to the very basic, assuming non-rotating metrics and stuff like that, assuming you had let's say a minimal black hole, so to speak, it would have 50 Planck areas. That seems very precise. Now, insert speculation on my part, and again, I didn't run the whole conjecturing ahead, but just speculation on my part. Where the heck could that 50 come from? I don't know. Well, maybe if we had 5 dimensions of measure, sometimes you square things. And if only you had could find a way to get 2 of them in, I have no idea. That's just rampant conjecture on my part. But that's pretty cool. Anytime you get a number like that, all right, surface gravity. What do we got here? All right, so we're kind of doing a little bit of an inversion. So we got C4 on top, speed of light to the 4th. We're dividing it by 4, which is interesting. Newton gravitational constants times our mass thingy there. So we throw in the Planck mass there. Okay, I confirm it's expressing in the right ways. All right, we get 1/4. Oh, isn't that a nice compact little formula? Cool. Okay, so we get this. 1.39 times 10 to the 51 meters per second squared. That's a ginormous number. But I do enjoy a good fortune cookie, Rick. That's sometimes maybe I should take them more seriously. But I always like hearing Wolfram. Sometimes it just gives you normally acceleration, but it's also gravitational acceleration. And then you look at that, and it's like you look at basically the equations for Hawking radiation and the Unruh temperature. They're more or less the same thing, except what's one? One is acceleration. The other is gravitational acceleration. So it's acceleration. Okay, cool. We may argue by why it's happening. Okay, so acceleration, length divided by time squared. Oh, and it gives us this number here, which we actually get into it right here, so we don't need to delve into that. Just notice that popped up. So temperature, basically we jumped ahead there, so we get speed of light to the 3rd there, which is interesting, times h bar, so Planck's reduced constant, so you divide that by a circle, or Planck's quantum of action by a circle, divided by 8 pi. Oh, okay, so we got like 2 spheres there, or something like that. Seems to be big in Einstein's equations. Cool. Times the gravitational constant times, in that case, that's the Boltzmann constant. And we toss in our mass, which we'll type in the Planck mass right there. We got all the stuff and things, line it up. All right. Oh, look, 1/8 pi. That's a really pretty thing. It's like 0.79 or 0.07, something like that. But our result here, 5.637 times 10 to the 30 Kelvin. That's a temperature. That's pretty hot. It's also within like 2 magnitudes of the Planck temperature. It's the Planck temperature. Square root of speed of light to the 5th times h bar divided by gk, not Godzilla versus Kong, but Newton gravitational times the Boltzmann's constant squared. Well, it gives us this, 1.47 times 10 to the 32 Kelvin. Okay, let's do a little computation. All right, since we're talking temperature, we strip off the dimensions, because Wolfram Alpha will sometimes yell at you if you have those things in there. So we just put those numbers that they gave us, we type them in, we put X, and we have Wolfram Alpha do the maths for us. So, hey, Nolan, what's going on? Hey, Nuno. Thank you for joining my friend. We're just doing all little basic things. Like I did this all on just like the website version, but I'm like, let me throw it into a notebook in case anybody wants to take a look and not have to have multiple tabs. But, all right, so we solve that here. What do we get? Oh, 5.13 there. That's a cool number. Not too big. Let's see if we can find a close form that might explain what's going on. Oh. I guess that would make sense if we got 8 pi. I mean, we did have an 8 pi literally there. It's like, That's cool. And technically, if you go into here, it's and again, those are estimates. I think we have five significant digits in there or something like that. Because technically, 89 CU. It's if I did for our own derivations, I'm sure that hits a lot of significant digits. I'm not sure the full accuracy and stuff like that. That's why we have the close function of the Planck constant, the monastery. Um, but different story, different story. I'm going down that rabbit hole later. All right, let's get to entropy because this is kind of really what got my noggin a jogging. And all right, so what's this? We got our 4 pi. So I kind of I'm visualizing like a sphere. We kind of got like a ball or something like that. All right, cool. Times the gravitational constant, big G. Times the Boltzmann's constant. Times our mass, which is the Planck mass squared. All over the speed of light times Planck's reduced constant h bar. All right. We line up our stuff and things. Let Wolfram Alpha compute for us 12.57 Boltzmann's constants. So that looks like a familiar friend. Let's just throw it into Wolfram Alpha. Let's see if it shows us anything familiar. Oh, it looks kind of like 4 pi. Kind of sounds like we got a sphere there or something like that. And again, it's what do we have here? Uh, we had our 4 pi right there, so it's like okay. So we got like a sphere of Boltzmann's constants. Are we talking about something taking its spherical form, not trying to assume any of the other stuff and things that seem to always be going on? Okay, we got a sphere of Boltzmann's constants. Okay, I mean that's pretty neat. Let's delve into the other things that it gives us. I have it right here. Okay, let's look at our entropy equivalent. Hold on, I'll just do it here. Okay, so this is approximately 18 times the entropy equivalent of 1 bit of information. Yada yada. I've done stuff on that before. Interpretation, absolute entropy. The corresponding quantity when we run this is 18 bits. Huh. Rick is right. Sphere is not a ball. I use those far too interchangeably. Uh, okay, so we are talking a surface. Okay, I stand corrected. So we should be talking a ball then. This is why I say spherical forms. Just because it's a catch-all. I can have a circle in there. Da 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 da. I apologize for fake science. All right. So 18 bits of information. When we run our little entropy, I think that's the Shannon entropy equation right there. I'm like, okay, 18 bits. So for a minimal, hold on, I wrote down the stuff here. Okay, so 18 times 1 bit. So for a minimal, okay, so for a minimal sphere, okay. So we're going to incorporate volume. We're incorporating. Okay, I feel better about myself because I would have had to rewire everything in my head. Okay, so apparently for a minimal black hole, according to the stuff and things on Wikipedia, the its entropy is essentially 18 bits. So a minimal black hole is 18 bit. 18 things. Where have we seen that before? And we'll leave it up there. I could continue to rampantly speculate about this or that, but I didn't put conjecture, so I apologize for that. Would have been okay. Oh, thank you, sir. All right, but I think that's pretty cool. Just because you start looking at these things, it's like, all right, if you're like, oh my god, I can't understand, because most of this comes from I'm hearing it's like, if you got a super ginormous black hole, and the Hawking entropy, temperature would be very, very low. And I'm told if it's wicked frickin' small, it would be really frickin' hot. Is that the black hole itself? Is that the effect of the black hole kind of just being there within its space time like environment around it? I don't know. But I think it's pretty cool, and if anyone wants to check it out, it's right there. You can toss all the things into the Wolfram Alpha, and hey, I mean, we got some freaking awesome tools. I'm just saying that I don't know what happens if some of all these smart folks of old. What happens if they had our modern tools, our computational power, our computers and stuff and things? We do. And so make the most out of it. So that's all I got right now. Peace out, everybody. Take care of yourselves. Physics Monastery has I'm leaving, I think this Tuesday to head back over to Utah. So if somebody's in the area, has any questions or anything or any ideas, hey, feel free to share them. I'm still trying to square away the website. We have some very interesting things coming. We're taking an interesting direction, and we'll see how it goes. But until next time, take care of yourself.